Okay, we're looking at the 9.3 quick check. So for each of these pairs, we want to say which one is larger, and we're going to circle that, and then we are going to talk about why that's true. So here for sodium and magnesium, we got to find them on the periodic table. We're going to see that they're next to each other, and as we go across, they get smaller. So that means that sodium is the larger of the two. Okay, why is it larger? Because it has a lower Z effective. Okay, I'm writing with my fingers, so it looks terrible. Okay, if I have chlorine and bromine, okay, find them on the periodic table. We see they're one above each other. Okay, and bromine is lower. Okay, and that's the one that's larger, and that's because it has more shells. Okay, sodium and sodium plus. Okay, every time you pull an electron, if it becomes sodium plus, it loses an electron. So it's going to have less repulsion, and that is going to make it smaller. So the larger one is sodium, and sodium, because it has more electrons with the same number of protons. So more electrons with the same number of protons. Sulfur and sulfur minus. Okay, if you gain electrons, okay, then you're going to have more electrons with the same protons. Same reasoning, it's just the negative is going to be larger than the neutral. Okay, F minus and neon, at first glance, it said that seems kind of random, but if you think about it a little bit, they're actually both have the same number of electrons. So F minus and Ne both have the same number of electrons, so they have the same electrons, same number of electrons, but fluorine is larger because it has fewer protons. Now with the fewer protons, that means they're not going to pull in on that cloud of electrons quite as much. It'll be a little bit larger. Okay, neon and sodium plus, again, those two are isoelectronic. They have the same number of electrons. But now which one has fewer protons? Neon has 10, sodium has 11. Okay, so neon's going to be the larger one. F and AS. If we look at them on the periodic table, we're going to find out that F is to the up and to the right of arsenic. Okay, so arsenic is larger. Okay, and it's larger for two reasons. Okay, because it has more shells. And that's where we know the up and down trend. And it also has a lower Z effective. Okay, so it's the same as, the first two, these two way up here. It's those two reasons. And sodium and beryllium, if we look at those, again, we're talking that sodium is to the left and down, and it's exactly the same reasons. Okay, it's got more shells, and it has a lower Z effective. Okay, look at the next questions here. We have F minus and Na plus. Which one has a larger atomic radius? Okay, and explain. Okay, F minus and Na plus, how do they relate? They both have 10 electrons. Okay, they are both isoelectronic with neon. Okay, they have the same number of electrons, but fluoride, has fewer protons. Okay, fewer protons. It has 9 protons, whereas sodium has 11 protons. So there's going to be less attraction. And therefore a larger size. Now when we look at F and Na neutral, okay, that's a different situation. So if we see F and Na, we have to visualize where they are in the periodic table, and fluorine is way over on the right side of the periodic table. Okay, sodium is over to the left, but it's down. So it's a situation again where sodium is going to be larger, and it's going to be larger because it has a lower Z effective. Okay, the Z effective for sodium is going to be +1, whereas for fluorine it's going to be +7, very high. Okay, and it has more shells. So sodium has valence electrons in the 3s, whereas fluorine, its valence electrons are in the 2p. So more shells makes it larger, and the fact that it has a lower Z effective to pull those in. Okay, now the last question down here has to do with successive ionization energies. Okay, why is each value larger than the previous value? Okay, every time you lose one electron, every time you remove one electron, so this first energy here is the energy to pull off the first electron to go from neutral to +1, and then we go from +1 to +2 and +2 to +3. Every time we lose one electron, the atom shrinks, okay, because there is less electron-electron repulsion. So less electron-electron repulsion. Okay, as each electron is removed, and therefore it's going to get smaller and smaller and smaller, and I just don't have, my finger's not good enough to write all that in. Okay, so each one is going to get more difficult to pull off because the electron is going to be closer and closer to the nucleus. Now, how many electrons are in the outer shell of this atom? Well, we look at these numbers and we say, okay, 786, 1500, that's bigger by about 700 or 800. And we go to here, it's about 1500. And here it's about another 1500. And then all of a sudden, this is 16,000. That is a huge jump all of a sudden. That's 12,000 jump. So that big jump means that we have just gone from the valence shell down to the core electrons. Okay, and the core electrons are closer to the nucleus, and they also have a much, much, much greater Z effective, because now if you go down to the core electrons, the number of shielding is way, way down. So it's much harder to pull this off. That means there were 1, 2, 3, 4 valence electrons in that outer shell, and that is 9.3.